All right, we're at section 19.4, work in thermodynamic processes. But before we get there, let's go back to chapter 8, all the way back to chapter 8, where we learned that energy is always conserved. You may not remember it, but this is equation 8.2. It's the conservation of energy equation, and it's the change in kinetic energy plus the change in potential energy plus the change in internal energy equals the work plus the heat added to the system plus the transfer by mechanical waves plus the transfer by matter transfer plus the transfer by electrical transmission plus the transfer by electromagnetic radiation. These are, we're going to concern ourselves with two of these transfers, matter transfer and electromagnetic radiation, and of course work and heat. Um, but let me minimize this so that I don't interfere with the any of the text that appears on the slides. Um, let's look at the work done on a gas. Here you have dW, a little bit of work is equal to F dot dr. It's a force times distance. That's what we know work as, force times distance. Well, it's a minus F. It's being pushed on the gas. Fj minus Fj dotted with dyj. Uh, J dot J is equal to 1, so you end up with minus F dy. Well, what is the force? Force is equal to pressure times area. Uh, and so it's minus pressure times area dy. Well, what's area times dy? Well, that's a little bit of volume. Area times a little bit of y is equal to volume. So the dW, the little portion of work, is equal to the negative pressure times the little bit of volume, the dV. So the total work is equal to the negative integral of the initial volume to the final volume of P dV. Um, okay, so here we repeat it. Work is equal to uh, the negative integral of the initial volume to the final volume of PdV. The work done on a gas equals the negative of the area under the curve. The area is negative here because the volume is decreasing. We're going from, here's the initial volume to the final uh, volume. So the volume is decreasing, resulting in positive work. There's positive work being done on the gas as this piston moves down. Now, if the um, the uh, if it were reversed, if the gas were expanding and pushing on the piston, then it would be negative work. All right, so let's, the work done on a gas in a quasi-static process that takes the gas from an initial state to a final state is the negative of the area under the curve on a PV diagram, evaluated between the initial and final states. Um, okay, now the path that you take is very important. We can look at these three different paths: A, B, and C, and in you can see in the first one a constant pressure compression followed by a constant volume process. So you can see that in this path the pressure is the same. It's the uh, as the volume decreases, the pressure stays the same, and then suddenly there's an increase in volume. In B, we have first a constant volume. There's a pressure increase, the constant volume, and then the final pressure remains the same. Let's read the brown box: a constant volume process followed by a constant pressure compression. So first the volume is constant, and then the volume decreases to V final. And then here is an arbitrary compression. Well, if the work is the area under the curve, then certainly the larger these would be B, then the next largest would be C, and the smallest would be A. So the path that is taken does uh, change the work involved. Let me get rid of my notes here. Okay. So work is equal to the minus uh, initial pressure times V final minus VI. Um, and he- uh, and here the same work is equal to minus PF VF minus VI, and it's gonna, um, oops, I'm sorry, I read those wrong. The first one is work is equal to minus P initial um, V final minus VI is, and work is equal to minus P final VF minus VI. And so work is equal to the integral of minus VI to VF, the integral of VI to VF times PdV. Uh, okay, let's, now the first law of thermodynamics says the change in internal energy is equal to the heat plus work. That is the first law of thermodynamics. Let me keep up with my notes here. Um, the internal energy, uh, so this is a special case of the law of conservation of energy, um, which it describes processes in which only the internal energy changes, and the only energy transfer are by heat and by work. Um, so the change in internal energy is equal to Q plus W. Um, the Let's look at so if Q equals W, then uh, if Q equals W equals zero, then the change in internal energy is equal to zero. This is for an isolated system. In other words, there's uh, no no heat is being transferred to the cylinder, and no work is being done. You're not changing the system. So the uh, internal energy initial is equal to the internal energy final, and when that happens, you have a cyclic process. So when the change in internal energy is zero, then the amount of heat is equal to minus the work, and it's going to equal out. So as you traverse this path, there's no change in internal energy. This is a cyclic process. Um, okay, now let's talk about isothermal processes. Isothermal, this blue line is an isotherm. That means that the temperature is the same. The curve is a hyperbola, and the PV equals constant. Well, PV equals nRT. If the T is constant, if the temperature is constant, we know that N, the number of moles, is constant, and the R is the universal gas constant. It is a constant. So if the temperature is constant, then PV has to be a constant. PV equals nRT is a constant. This is an isothermal process. Um, and the change in internal energy is equal to zero. Q, the heat of the system equals to uh, the negative of work. Okay, let's see, the work equals the negative of integral from initial volume to final volume, PdV. Well, it's equal to the negative of the integral of VI to VF. Well, if nRT is constant, we can pull it out of the integral, and we end up with the work is equal to minus nRT times the integral from initial volume to final volume of dV over V. Well, if you look it up in your uh, uh, integral table, you'll see that this is ends up with a natural log of V. Um, so it equals to uh, negative nRT natural log of V evaluated from V initial to V final. Um, so the work is equal to nRT times the natural log of V final, uh, V initial divided by V final. This is isothermal process. Okay, isobaric process. Now, isobaric, we think of the sometimes the pressure on the news is given in uh, bars, millibars, um, you know, barometric pressure. Well, they all have the word bar in it. So isobaric process is a constant pressure. So you can see that the volume is constant. Um, so the W, the work is equal to minus P times the V final minus V initial. This is an isobaric process. Um, uh, and that's it for that. Then we have an isovolumetric. You can see that it doesn't change. The volume doesn't change. Only the pressure changes. And not only does the pressure change, notice you have a T1 and a T2. So that is, you have both um, a pressure change and a temperature change. So the change in internal energy is equal to Q. It's the heat added to the system. Adiabatic, um, adiabatic is the no energy enters or leaves the system by heat. That's an adiabatic process. So the change in internal energy is equal to W. There is no Q. Okay, so let's do a little quiz here. In the last three columns of the following table, fill in the boxes with the correct signs, plus, minus, or zero, for the heat, the work, and the internal energy. For each situation, the system to be considered is identified. So the situation is rapidly pumping up a bicycle tire, and the system is the air in the pump. Well, if you do it rapidly, there's no, Q is equal to zero. The work is plus, you're doing work on the piston, and the internal energy is plus. So you're gonna, if you pump it up enough, you'll feel if you grab the cylinder of your pump, you'll feel it's warming up. So zero plus plus on that one. The pan of room temperature water sitting on a hot stove, and the system is the water in the pan. Well, if it's on a hot stove, you're adding Q. You're heating the system, so that's plus. Uh, if you're not, there's no cylinder, there's no piston pushing on the water, so the work is zero. And of course, the internal energy it's going up because you're adding heat to the system. So that's going to be plus zero plus. And then we'll talk about air quickly leaking out of a balloon. The system is the air originally in the balloon. Well, there's no heat being added to the system, so that's zero. And there's no work. Well, actually, the work is negative as the air leaves the balloon. It's doing negative work, and the internal energy is decreasing. So we have zero plus plus, plus zero plus, and zero minus minus. And let's see if, yes, zero plus plus, plus zero plus, and zero minus minus. Now let's look at some uh, curved line or some lines here. Characterize the paths in the figure as isobaric, isovolumetric, isothermal, or adiabatic. For path B, the Q is equal to zero. So there's no heat. There's no heat being added to the system. So the A, you can see that, well, the volume, this is the volume, so the volume is the same, so it's isovolumetric. B, it says Q is equal to zero. There's no heat being added to the system, so that's adiabatic. And then C, well, you can see it stays along the T3, the temperature 3 line, so it's isothermal. And here D, the pressure remains the same, so it's isobaric. And that's path A is isovolumetric, path B is adiabatic, path C is isothermal, and path D is isobaric. And I think that's it for this section. I apologize that this video went kind of long, but that's okay.